just remind ourselves where we were. We're reminding ourselves how place value arithmetic worked, or place value number systems. And something like 1832, where's my water bottle? I bet I left it in the damn car. Okay, well, frack. All right, sorry. So, how do we decode the values of numbers, right? So if I write down the sequence of digits 1832, you guys understand two things. One, which end is the big end and which end is the little end? The leftmost is the big end and the rightmost is the little end, okay? And so what we say, by the way, then, is that we write our numbers in big Indian, okay, as opposed to little Indian. So we write the largest, most significant digit first, and then we proceed to the right from there. Now, that looks like a really creative word, right? Which end do we write it out? The big end is first. Okay, I am not making that up. That is actually the word that we use for it. Now, here's the pop quiz. Does anybody know where this term came from? And it was not computer scientists. It's much older than that. In some sense, yes. It's from a novel. Looking at my favorite British subject. How many of you guys have read Gulliver's Travels? Yeah? So do you remember the big and little Indian battles in Gulliver's Travels? Yes. A computer scientist who was well read used the terms from there, and then it stuck, right? So in Gulliver's Travels, there's two groups of people, and they basically wage holy war against each other over which end of the egg do you crack, the big end or the little end? Yeah, and so that we use the term then from that. So we tend to write numbers in the big Indian order, meaning that the largest, most significant part is written first on the left, and then we go to the right from there. Now, we also write in base 10 because that's the number system that we use. But to some extent, you guys actually are used to using other bases of number systems. We talked briefly at the end last time that you're all accustomed to using dozens as a unit. And even in English, the words for counting from 1 through 11 or 1 through 12 are a separate counting word system until you hit 13, when it changes to the teens construction, okay? So you're used to counting in dozens, and in fact, we're also used dozens in some other ways. How many hours are on the clock face? 12. Okay, it really should be 24, damn it, but alas. On an analog clock face, it's 12. You also are in some sense used to using base 60 for what? Yeah, degrees, minutes, right? You use them in basically measurements of circles, and because of that, also measurement of time, because it turns out that, well, time and circles are related because of astronomy. Okay, so you're also used to that. So is it really all that big of a deal to switch number systems to something different? Okay, and we're going to look at two of them. Base 2, or the binary system, and base 16, which is called hexadecimal. Okay, now in these two schemes, in binary, what are our digits? That's it. Everything will be expressible in terms of those two digits only. And in hexadecimal, we have the same digits 0 through 9, but we need 6 more, hence the name hexadecimal. And the convention that is stuck is to just use the letters from there. Okay, So we'll start with binary, and then we'll build into the hexadecimal. These number systems, or the realization that you can do these number systems, is actually pretty old. In fact, just yesterday I was reading excerpts of, how many of you guys have heard of Gottfried Leibniz? No? How many of you guys have taken calculus? Yeah, he's one of the two people that kind of cooked it all up, in some sense, him and Newton. But, you know the symbol for an integral? Leibniz came up with that. He's evil? No, he's polymath. Okay. Anyway, so we'll start with the binary stuff, and then we'll get into hexadecimal. I think you guys will see the utility of having both of them. So there was a joke I told you guys at the last time, which was, how many types of people are there in the world? 2, right? But how did I write it? Oh, I didn't write it, did I? I just said it. Okay. So there are 10 types of people in the world. Those who understand binary, and those who don't. All right, and it's funny because when you look at that, what do you immediately think? You think 10 because you're used to numbers being written in base 10, and so you just automatically think that. Okay, so this is funny because in binary, 1, 0 is actually how you write 2. Okay, and here's the system. So in the same way that, what are the place values in base 10? What's the far right position? The ones place, or the 10 to the zeros place, and then after that is the tens, hundreds, thousands, and so on, right? Well, it works exactly the same way, except this time, instead of being powers of 10, it's powers of 2. Oops, second comes next. Okay, so the values, of course, are 1, 2, 4, and 8, and of course we can keep going however long we want. And so if I have a 1 in the 2's place and a 0 in all the other positions, then that's why it means 2. Okay? All right, now, how do I know if I'm looking at a given number that it's written in base 2 versus something else? Right? If I just wrote down, well, like I did here, 1, 0, right? It's in some sense ambiguous. Is that base 2 or base 10 or base 16 or base 20 or base, who the heck knows? It's not clear, right? So I should probably start specifying from here on what base I'm writing in so that it's not, not confusing. Okay, make sense? Yeah. All right, so the way that I'll do that is if I write a number in binary, I'll do one of two things. I'll either write 0b and then the number. Okay, so that's not the digit 6, it's the letter B. Okay, or I'll say 0010 base 2, and I'll write that in like actual letters. Because if I write the symbol 2, well, then what the heck does that mean? Okay, so something like this. This indicates it's in binary, not in base 10 or something else. Okay, and that way we won't get confused when we write down numbers. Okay, yes, sir. 2. Yeah, the base 10 value 2. So this represents 2 in base 10. Okay. And so what I want to be careful about here is to say that the binary number, I'm not saying that it is 2, I'm saying that it's a representation of 2. And that distinction as to value and representation will become kind of more clear later. why we need to make a big fuss about it. Okay. Um, okay, so let's just start writing some numbers and figure out how we would write them in binary. Well, let's start with 1832, actually. I mean, that's maybe too big of a number to do it, but why not? So in order to do this, what's the biggest power of 2? In fact, let's just list the powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, and so on. Okay? And I don't know how many guys have played that little game called 2048. Yeah. Okay. So where every time you double and it's yeah. All right. So those are the powers of 2 up to well, however many of them. And the way I'm going to take a base 10 number and encode it in binary is to say, well, what's the largest power of 2 that I can fit into it? So if our number is 1832, so let me write it this way: 1832 is 1024 plus how much is left over? This is where we have to start thinking or just bust out a calculator. Huh? How much is left after the 1832? 8, 12? Yeah. Okay. And then 812, what is it? 808, yeah. So if I wanted to be good at arithmetic, gentlemen, I would have become an accountant, a mathematician for a reason. I can do calculus in my sleep, but ask me to do subtraction, woof, all bets are off. All right, so 808 is the remainder. Yes, we're clear with that? Okay. All right, so 808, how many 512s, so the next smallest power of 10 can I fit into it? 1, okay. And you'll notice that you can never do more than one of them. If you have 2 or more, that means you're not using a big enough power. Okay. And what's the remainder this time? 296. Somebody who has a calculator handy, double check our arithmetic just to make sure we're not flubbing it. Huh? Yeah? Okay, 296. Can I fit a 256 into that? Yep. And fortunately, this one's easy. With 40 left over, 40 is 32 plus 8. 8 is 8, and then no remainder. Okay, so I'm finished. Okay, so what I've done is figured out which positions I have a 1 in, and the ones that I haven't written down are going to be zeros. Okay, so if I write this in order, so I'll have 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, and let me write the values. So 1, 2, 4, 8, 16, 32, and I need to keep going. All right, 2 to the 6th is 64, 2 to the 7th is 128, 2 to the 8th is 256, 2 to the 9th is 512, and I'm sorry my handwriting is so messy this morning. 2 to the 9th, 512, 2 to the 10th is 1024. Okay, so did we use a 1024? Yes. Did we use a 512? Yes. Did we use a 256? Did we use a 128? No, no, yes, no, yes, no, no, no. Okay, and there's our number. Okay, good. Now, going the other direction is actually, I think, easier because you do less thinking. You just add up the corresponding powers, right? So how could I double check if this is correct? I could say, all right, what's 8 plus 32 plus 256 plus 512 plus 1024? Does that add back up to 1832? If so, I've done this correctly. If not, we've screwed something up. Okay? So not too horrible, right? You just have to sit down and think a little bit. And of course, having a calculator handy to help with the arithmetic just so that you don't screw it up is certainly a useful thing. Okay, so questions, preguntas, fragen there. Yeah. So what's the advantage to writing 1832 in base 10? So here we have 1832 in both base 2, and you know what it looks like in base 10. What's the advantage of writing it in base 10? It's a lot shorter. There's only 4 digits. Whereas how many bits do we have here? 11, because we start with 2 to 0, right? So the disadvantage of binary is that the numbers are real long. The advantage is that how many symbols are there? Just 2, ones and zeros, okay? And so that advantage from a computing standpoint is precisely what we want, because what logic states do we see when we're building our gates here? Basically, there's just 2 states, off and on, okay? Now, I say basically because I've actually kind of lied to you guys. How many states are there between 0 and 5 volts? Strictly speaking, infinitely many, right? Because how many voltages are there between 0 and 5 volts? Infinitely many, right? Now, a lot of them are really close to each other, right? 2 volts and 2.00001 volts are effectively the same, right? But the logic states that correspond to high and low aren't perfectly 0 or perfectly 5 volts ever, right? It's just sort of above a certain threshold and below a certain threshold. And if we're non-idiots in terms of wiring up our circuit, we never have voltage values that are kind of in that mysterious, ambiguous zone in the middle. Okay, it's either high or low. And so if it's 4.9 or 5.1, like, close enough, it's 5 volts, right? And so this is why we can treat the transistor things as being just on or off, because it's essentially 0-ish volts or 5-ish volts, and as long as the ish isn't too imprecise, everything works okay. Okay, so yeah, so then with this, right, this is nice because if I want to, well, if I have some sort of circuit, right, these bits actually mean something in a physical sense of something either being on or not, right, or 5 volts or 0 volts. Okay, so that's the advantage, I guess, of using binary, is that it's perfect for doing things with electricity, right, where you have just 2 states, that's it. Okay. Now, I should say that there are circuits and components that use multi-state things. So a good example of it would be, how many of you guys have bought an SSD in the not too recent past? Yeah? What'd you buy? Like an external thing? Okay. Anybody bought a one for inside a desktop or laptop recently? Yeah? So what'd you buy? Right? All right. Which one? Was it quad level, tri level? Yeah, you don't know. Okay. That's all right. So some SSDs actually can use uh, multiple levels of encoding, and by doing so, they can store more data in a denser package. Um, and it comes with trade-offs, but it also the benefit is storage density, which means that your chip can fit more than it would otherwise. Okay, so anyway, back to the binary stuff. So it's impractical, at least for us as humans, to actually write out all these bits, right, as you've seen. And bit, by the way, stands for binary digit. Okay, it's the smallest unit that you can have. A bit is either a 0 or 1. Okay, so I've got this big long number, and do I want to have to write out that number in that form all the time? It's kind of inconvenient. Okay, so this is where hexadecimal comes in, because in some sense we can use it as a shorthand. Okay, so I'm going to have to move to a clean sheet. So any questions on the conversion process before we move on? Okay, it's not hard, it's just you have to do some arithmetic. Okay, so how many different bit patterns are there if I have 4 bits? 16-bit patterns. And that happens to be 2 to the 4th, right? This is basically asking the same question as if you flip 4 coins, how many different possible outcomes are there going to be, right? They could be all heads, they could be all tails, and then there's 14 different mixes inside. Yes? Okay, so let's list out all 16 of them. And I'm going to list them out in a very particular order that the secret sauce for which I will not reveal immediately. And I do this out of kind of muscle memory at this point, so just bear with me for a second. All right, there's the first 8. Now, if you stare at it for a minute, you might be able to start to see the pattern that I'm doing. And if not, well, perhaps all will be revealed shortly. All right, let me keep going. Sorry, I've already screwed up. Oops. All right, there's all 16 of them, and let me zoom out so that they all fit. Okay, so what's the secret sauce of the order that I put them in? Well, let's think. What's the first one represent? Probably 0. Yes? Okay. And what's the one after that represent? And the one after that? 2, and so on, right? So if we decode these the same way that we did our 1832 number, I'm just counting here 0 through 15. Yeah? And so the one at the bottom, how do I know that that's 15? Well, how many 8s or how many 1s do I have? 1. How many 2s? 1. How many 4s? 1. How many 8s? So what's A plus 4 plus 2 plus 1? 15. We? Okay. So what are the values, or the either values or what am I going to use to notate these? I'm going to call this one 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Uh-oh. What's the next one's value? 10, right? I'm not going to write 10. I'm going to write A, B, C, D, E, F. Okay, now how many of you guys think that that's insane? Huh? Not really. It's not insane. It maybe it's a little atypical, right? But the reason I want to do that is because I want every 4-bit pattern to have a single symbol associated with it. If I write 10, 11, 12, and so on, I'm using base 10, and I'm trying to avoid using base 10. Okay, so here what we have is called hexadecimal, right? And it is a shorthand. In some sense, you can think of it as a shorthand for binary. Each hexadecimal character is sort of equivalent to 4 bits. Okay, and you'll see the utility of this in a moment. Okay, now the other thing is that does it make sense the order that I wrote them in? right, was in somehow an increasing order. Yeah? Okay. So there's no really secret sauce to it. That's just the order I put them in. And it's certainly a logical order. It's not the only order I could have put them in, but like, don't be stupid. Don't just randomly do it or you'll miss some. Okay. Um, okay. So let's take this and let's take our 1832 bit pattern, whatever we got a moment ago, and let's put these ideas together. Okay. All right, are we good? Let me know when I can move on from the table here, although it's not hard to reconstruct. Am I good to go on? Okay. Looking at my favorite left-handed person over there. Left-handed people. How many of you are left-handed? All right. Out. All right, what did we get for 1832? Let me just copy and paste it. And in the magic of using an iPad to teach, right? Well, that turned out like crap, didn't it? All right, can somebody just read it off to me? Oh, hold on, sorry. 11100, like that? There we go. Okay. So what I'm going to do is I'm going to chop this into groups of four, starting from the right. And you'll notice that what I just did, actually, let me write it in a different color so it's obvious, is how many bits did I originally have when we encoded this? I only had 11, okay? So I've padded it with a 0 to the left so that they come in multiples of 4, okay? And in computing, we'll actually pad with enough zeros so that we're not just a multiple of 4, but an actual power of 2, right? So I would pad this thing with 4 more zeros probably so that it required 16 bits or maybe even more. Okay, so fine. So I've split it into chunks of 4, and then within each chunk, I'm just going to decode what are that 4-bit pattern, which hex character does it align with? Okay, so what do the three of them align with? What's this one? 0, 1, 1, 1, 7, and then the next one, 2, and then the next one, 8. Okay, so 728 hex is 1832 base 10 or decimal equals that bit pattern in binary. Okay, so these are 3 different ways of writing the exact same number in these different systems. Okay. Now, with 728, where is the 8? Which position is he in? He's in the ones place. It's always the ones place for the far right, dude. Where's the 2? Huh? Ah, but this is base 16, not base 10. So it's the 16's place. And where's the 7? What's 16 times 16? The 256's place. Okay. All right. So let's double check that we've actually encoded this right. What is 7 times 256 plus 2 times 16 plus 8? Does it add up to 1832? It does. Huh? That's crazy? No, that's just math, right? Okay, how many minds are just going? Yeah. Yes, Jojo, go ahead. A what now? No, because what is A? A is like 10, right? Okay, so yeah, so let's take Jojo's question, right? Let's suppose that I have the hexadecimal number AF, right? This is a big number. It's big AF. Um, yeah, you guys see what I did there, right? Okay, so what is this? This is A times 16 plus F times 1. Well, what's A? 10. And what's F? So this is 10 times 16, which is 160, plus 15 is 2, what now? What is it? I can't do arithmetic this early. 160, 175? There we go. That's fine. So even if it's a letter, it doesn't matter. Just use its corresponding value for the conversion, right? Okay, now why the letters drive you guys crazy is because they're not part of the usual decimal symbol system, right? You're very accustomed to using 0 through 9 as digits, and I'm just saying, okay, now imagine a world where I'm going to throw in 6 more symbols, and rather than having to make up 6 new symbols, I'm just going to recycle the alphabet. Yeah, I could have made up 6 new symbols. And we could even imagine, what about if we were from a civilization that just did it this way from the get-go, right? You would find base 10 weird and base 16 to be perfectly natural because that's what you used all your life. You know, what makes this uncomfortable is the fact that you're all at least 18. You've been using base 10 arithmetic for 18 years, and now suddenly in 30 minutes, I've just thrown 2 new number systems at you and said, okay, have fun, or good luck, everybody else. You know, the Family Guy cutaway gag with the lady in the car. No. Good luck, everybody else. Okay, never mind. Anyway. Um, okay, so yeah, this isn't really that hard, is it? You just have to kind of think a little bit. Okay, so with respect to our 1832, right, what are the different utilities here? For us as humans, what's an easier way to write it? Well, just as 1832. That's probably the easiest, okay? But if I want to look at it in binary, it required, well, what, 11 bits here? Maybe more if we pad it. 728 is useful enough because there's a direct correspondence between it and the binary that's obvious, right? Each binary or each group of 4 bits is exactly one hexadecimal symbol, right? So, and you don't have to think as much to go between hex and binary. That's why hex is so useful in computing, okay, as sort of a shorthand, if you will, for binary. Okay, is that all right? Yes, Jojo. You can. It's just so, like for example, I wrote AF, right? That's a hex number. What binary does it equate to? Well, I haven't written it down, but I certainly could, right? Because what's A? Yeah, 1010. And what's F? 1111. Okay. And that bar that I'm putting in the middle is not actually there. I'm just doing it in writing so that it's easy to see the groups of 4. Um, so I wouldn't actually write that in practice. Okay. Um, I just do it to make it easy to separate out the groups of 4. Okay. So that's why hex is so useful, is because I can immediately, almost without thought, expand it into its equivalent binary form. And if I've got a binary form, almost without thought, I can go to hexadecimal. Going through base 10 requires thought. Okay. And the reason it requires thought and the other ones don't is because 16 is already a power of 2, right? So if I've got one system that's built off powers of 2 and another system that's built off of powers of 2 to the fourth, then the conversion between them is easy. Okay. Okay, so does that make sense? So if you guys ever wondered, well, how many of you guys have Xboxes or something like that you've had to get on the Wabash IoT network? And what do you have to do to get something on the Wabash IoT network, pray tell? You got to put in the MAC address, the hardware address of the Wi-Fi part, right? And what is that? It's all in hexadecimal, right? So it is 6 groups of 2 hexadecimal characters, right? So 12 hex characters, and therefore 48 bits, right? And each device gets its own, like this laptop's Wi-Fi chip and that laptop's Wi-Fi chip have different hardware addresses. Now, they're similar to each other because they're made by the same people, right? Although with iPhones now, actually, I didn't realize this until at least one version ago or so, it actually will randomize the hardware address on the Wi-Fi. And so when you go to like Starbucks or something, it's a random address every time, which is kind of annoying, but you can turn that off, by the way. So yeah, but that stuff, that big string of things that you had to put in that had digits and letters, you were typing something in hexadecimal, right? So see, you guys already know it. Wabash IoT. Um, Although really, you shouldn't be using Wabash IoT because if you're going to have an Xbox connected, what should you be doing? Ethernet, bro, Ethernet. Okay. Yeah. Anyway. Um, okay. So not too horrible, I hope. Yeah. So the utility of this, at least as of right now, right? So we've put together circuits that took how many inputs? So far, only 2. Okay. But could we imagine having circuits that had 32 inputs? Okay, we need a lot of breadboards, right? Or conceptually, we can think of them. Okay, it starts to get unwieldy to think about the individual binary stuff and more useful to think about in this sort of shorthand, the hexadecimal. Okay, so that's, yeah, okay. Now, let me just, for sake of demonstration here, just kind of show you a few instances where we can use this sort of thing. All right, so let me open up a terminal. Well, I'll just do this one. How about, okay, so for example, in programming classes, I want to, well, and we'll continue with this discussion as we go, we want to understand how does data actually get stored in a computer, okay? And so what kind of data could we store in a computer? Numbers? Pictures? Okay, let's think more simple forms of data first off. So how about numbers and text, right? And anything else we can build out of one of those 2, right? Pictures are really just a crap ton of different numbers for this pixel, red, green, blue, that pixel, red, green, blue, and so on, okay? Okay, so numbers and text. How are these things encoded? Well, the numbers, in some sense, we've kind of dealt with, not completely, okay, and we'll continue that discussion Wednesday. But also within the numbers, well, what kinds of numbers are there? Okay, odd and even, that's certainly a division of which class of numbers. So odd and even belong to which sort of larger group? what's the word for that larger group? Huh? Whole numbers or integers, right? Same thing, right? Integers is more, it scores you more points in Scrabble, okay? So we use that one instead. Yeah, so integers, right? Well, within integers, and this actually will make sense a little later, we could really think about two different versions, signed and unsigned, meaning allowing the possibility of negative numbers or not, okay? And there's utility in having both versions. Um, but what other kinds of numbers are there besides integers? Yeah, decimals or fractions or however you want to put it, basically real numbers that aren't integers, right? So 2.5. How do I encode 2.5? And in particular, when we write 2.5, what have I used there to indicate something? A decimal point. Well, if I'm trying to encode everything with only ones and zeros, where's the decimal point? This is a little more tricky than you might think, right? So floating point numbers is what we call those, right? Um, and how do we do that? Well, we'll get there. What about text? So I have here the source code for a program from one of my other classes, and I've done what's called a hex dump on it, which is I've literally taken the file and I've said, okay, I want to see the entire file, just dump it in hexadecimal. So the very first byte of this file is this value, 2E, that happens to correspond to the period. Okay. And now how do I know it corresponds to the period or that the next one, 6.4, corresponds to lowercase d? Well, there's a system for it, and we need to talk about that system. It's called ASCII, by the way. Um, and yeah, so we'll go there. So text, numbers, and there's multiple different categories of numbers that we need to worry about. And then bigger, more compound things are just going to be somehow groupings of these things that we've already established. If we can figure out how to do a single number, then we can figure out how to do a bunch of numbers. And a picture is, in some sense, just a bunch of numbers. A movie is a bunch of numbers put together in some sort of logical way. Okay, so does that kind of make sense? Yeah? Okay. So let's go back to the iPad for just a moment and start to talk here about write down our categories of data that we want to deal with. Okay, so we want to deal with numbers, and these are going to come in two flavors, integers and floating point. And the integers can either be unsigned or signed. Okay, so we already have three different categories of things to study. Then we'll also look at letters, which would be characters. Okay, and there's there's several standards for doing that, but we'll look at the sort of earlier version, which is a little simpler, called ASCII. There is also a more modern system called Unicode. How many of you guys have used a Unicode character in the last 24 hours? How many of you guys have used an emoji in the last 24 hours? Those are all encoded in this thing called Unicode. And we'll talk about why we needed something beyond ASCII later. Okay, so we'll deal with the numbers stuff for a while, and then we'll move on to the text. Okay. Okay, so unsigned integers are the easiest to deal with because we're not going to include anyway the possibility of there being negatives. We'll just have numbers. That's it. Okay. So those work basically what we already did. Okay. So for example, let's go back to the previous page. right? All of the numbers that we were dealing with here had no concept of negative associated with them, right? They were all positive or zero, and so we call those unsigned. And there are lots of situations in which having unsigned numbers makes complete sense. For example, if you're counting objects like inventory in a warehouse, does it really make sense to have negative parts? So why store the idea of negative? Okay, as long as you can do subtraction, meaning you could deduct that, say, you've got 15 widgets and the customer comes in and buys two, well, now you have 13 widgets. So as long as you can do that, then you're okay. The sign stuff will be kind of interesting. And to motivate that, I want to start with a magic trick, and I'm going to leave you guys puzzled over that magic trick for the next 2 days. Okay. All right. Somebody give me two two-digit numbers. Base 10. 2 and 5. Okay. Could I have maybe two-digit numbers instead of one-digit numbers? Huh? Okay, fine. 20 and 50. What's 50 minus 20? 30. Okay. That's not the magic trick, by the way. Okay. Right. Okay, so the magic trick is this. I'm going to take the number 20 and I'm going to mirror all of its digits. 0 mirrors to 9, 1 with 8, 2 with 7, 3 with 6, and so on. All right, so I'm going to take that, and what's 2 mirrored with? 7. What's 0 mirror with? 9, and I'm going to add 1 to that. Okay? Then I'm going to take the original number that was given to me, 50, and I'm going to take 80, and I'm going to add them. And I get a carry, which I'm going to throw away. And I get exactly the same thing. Have I bamboozled you? You made up the numbers, right? Make up another set of numbers. I'll do it again. How about 78 and what? 78 minus 34. Okay. 44 is, of course, the answer. All right, what's 3 mirror with? 6. What's 4 mirror with? 5. Add 1. 66. So I'm going to do 78 plus 66, and I get 14, carry the 1, 7, 4, carry the 1, throw it away, 44. Right? Yeah. Okay, so why this works and what the utility is of it, we'll start with on Wednesday. Okay? For that now, you have to ponder why it works.